Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. Imagine the vast emptiness of space. At first glance, it might seem like nothing, a silent, endless void. Yet physics reveals a subtler truth. Even in regions stripped of matter and light, space is never truly still. Invisible fields ripple, energy shifts imperceptibly, and the very fabric of spacetime vibrates with quiet motion. These are not mere speculations. They are the discoveries of decades of careful measurement, from particle accelerators on Earth to telescopes peering across the universe. Tonight, let us drift gently into the heart of the cosmos, following photons as they travel. These are not symbols on a page, but delicate voyagers, gliding with extraordinary sensitivity through the contours of spacetime. Their journey maps the boundaries of how restless the universe can be, and in tracing their path, we begin to see which ideas about reality withstand the test of observation. Start here, in this calm moment, and consider this quiet truth. Empty space is never entirely still. Its subtle restlessness is not accidental. It is essential. Remove every particle, every photon, every trace of heat or charge, and something still remains. Instruments detect it. Faint patterns, gentle fluctuations, the hum of the universe itself, whispering the story of the energy underlying all things. At human scales, emptiness appears convincing. Between stars, there may be a single atom per cubic centimeter. Between galaxies, even less. Classical intuition suggests this is nothing. Yet precision tells a different story. Quantum fields pervade every corner of reality, even when particles are absent. They are the framework of our calculations, allowing predictions, such as the magnetic moment of the electron measured at CERN and SLAC, to match observation down to astonishing precision. Remove these vacuum fluctuations, and the predictions collapse. The quantum vacuum is far from empty. It is the quietest state of energy, the calm surface of a restless sea. Fluctuations endure because energy and time cannot be known simultaneously with absolute certainty. This is no philosophical fancy. It is repeatedly confirmed by experiment. In 1948, Hendrik Casimir predicted that two uncharged plates, placed mere micrometers apart in a vacuum, would gently attract. With no charge, no magnetism, no gas, the force arose purely from the dance of quantum fields. Vibrations between the plates were constrained, lowering energy in that space and producing a subtle pull. Decades later, experiments confirmed the effect. Even emptiness responds to geometry. Even the void has structure. These patterns are not confined to laboratory tables. On cosmic scales, the restless vacuum leaves its imprint. The cosmic microwave background, mapped with exquisite precision by NASA's WMAP and ESA's Planck, shows temperature variations of just 1 part in 100,000. These tiny ripples are the memory of quantum fluctuations from the universe's infancy, stretched across billions of years and amplified by gravity, sculpting galaxies, clusters, and the vast cosmic web. Space itself seems to remember. Photons are the universe's quiet messengers. Weightless and unfettered, they trace spacetime's subtle geometry, responding to every curve and fluctuation. A photon has no rest frame. It moves entirely according to the structure it encounters. Light traveling from distant galaxies, or into the detectors of the James Webb Space Telescope, chilled almost to absolute zero, carries a record of its journey. Over 13 billion years, these photons have traversed expanding space, past massive cosmic structures, and yet remain coherent, with sharply defined spectra. If spacetime were chaotic, if geometry shifted too violently, their phase would fray, spectral lines would blur, arrival times scatter. But none of this happens. The universe allows motion, yet imposes order. Now, we arrive at a subtle tension in the universe. Quantum fluctuations carry energy, and energy, according to general relativity, shapes the fabric of spacetime. The result is inevitable. Spacetime cannot remain perfectly smooth. Energy nudges geometry, geometry responds, and the two are entwined in a delicate, perpetual dance. In the 1950s, John Wheeler imagined what occurs at the tiniest scales. Spacetime itself, he proposed, would seethe with wild fluctuations, a froth of geometry he called quantum foam. At such scales, our usual ideas of distance and time no longer hold. To measure it directly would require energies so extreme that spacetime would curve in response, and the very act of observation would disturb the phenomenon being measured. This threshold is set by nature itself. The Planck length, a vanishingly small scale derived from the speed of light, the gravitational constant, and Planck's constant. Here, notions of precise location or exact moments fade. The limit is not arbitrary. It emerges from the structure of reality, confirmed independently across multiple theoretical frameworks. Both quantum mechanics and general relativity point to the same truth. At its smallest scales, spacetime resists being pinned down. So as you settle into the rhythm of this story, picture the universe as a living, breathing expanse. Empty, yet full. Calm, yet restless. Photons, tireless travelers, weave through this terrain, carrying the memory of creation. Spacetime bends, ripples, and hums beneath their passage, teaching us that even in seeming nothingness, there is depth, there is motion, there is life. Let your mind drift along with them, feeling the quiet persistence of the cosmos, from the subatomic to the cosmic, and allow that understanding to bring a gentle calm. Imagine the universe as a vast, responsive fabric. Space is not a passive stage. It resists being treated as fixed. And here, photons guide us. Sensitive to the tiniest bends and ripples, they traverse geometry with exquisite care. The smallest imperfection, theory predicts, might accumulate across billions of light years, slightly altering arrival times or scattering light. In practice, such deviations are nearly imperceptible, but across cosmic distances, even the tiniest effect could be revealed. To test this, scientists turn to some of the universe's most dramatic events, gamma-ray bursts. These fleeting, brilliant flares emit photons across enormous energy ranges in a fraction of a second. NASA's Fermi Gamma-ray Space Telescope has observed them for over a decade, capturing light that began its journey billions of years ago. And the result is striking. Photons of all energies arrive almost simultaneously. Across the vast, expanding universe, no lag appears. The simple predictions of chaotic, jittering spacetime are nowhere to be seen. Many early models of quantum foam are quietly ruled out. The lesson is clear. Spacetime may quiver with tiny fluctuations at microscopic scales, yet across observable distances, it behaves with remarkable discipline. Lorentz invariance, the principle that the laws of physics are the same for all observers in uniform motion, remains intact. From laboratories and particle accelerators to telescopes and atomic clocks, symmetry endures. The universe is restless, but ordered. Activity exists, yet it balances perfectly, averaging out to maintain harmony. Classical physics imagined space as inert. Einstein revealed it bends and curves in response to energy. Quantum theory showed that even emptiness can never be fully at rest. Modern physics unites these truths. Space participates, but within strict limits, constrained by symmetry and consistency. Even gravitational waves, ripples in spacetime detected by LIGO in 2015, confirm this balance. They carry energy across millions of light years, deforming geometry, yet maintain coherence. Space can move, vibrate, and stretch, and still obey precise rules. Photons do not move through emptiness. They traverse a structured, vibrant environment shaped by quantum and gravitational principles. And yet, mysteries remain. At the smallest scales, where geometry must fluctuate, spacetime hints at its deeper nature. Some theories suggest it is made of discrete units. Others propose that geometry itself emerges from patterns of quantum information. No single model has been confirmed, but all must respect what photons reveal: the coherence of light, the order of the cosmos at accessible scales. Here emerges a boundary that recurs in every investigation, a scale where smooth spacetime can no longer be taken for granted. This boundary is not philosophical. It appears when our trusted theories are pushed to their limits. Spacetime does not erode gradually, it falters sharply. At ordinary scales, everything behaves as expected. Lengths can be measured, durations compared, events ordered. General relativity maps gravity accurately. Quantum mechanics governs atoms, radiation, and fields to astonishing precision. Yet as we probe smaller scales, certainty begins to waver. Uncertainty in quantum mechanics grows as we attempt to pinpoint a particle. The energy required to localize it distorts spacetime itself. At a certain threshold, geometry reacts, disturbed by the very act of measurement. This is not a glitch, it is a fundamental limit of nature. Combining the speed of light, the gravitational constant, and Planck's constant gives the Planck length, about 1.6 times 10 superscript 3 meters. At this scale, the notions of distance and time lose meaning. To go further would demand energies that could form tiny black holes. Smooth spacetime is no longer a valid assumption. What is remarkable is that this boundary appears independently. General relativity reaches it when curvature is extreme. Quantum mechanics reaches it when uncertainty overwhelms localization. Two theories, born from different principles, converge on the same frontier. This convergence is not coincidence, it is a signal of the universe's deep consistency. Think back to the early 20th century. Einstein reimagined gravity as geometry, space and time bending and flowing in response to mass and energy. Quantum mechanics emerged separately, revealing the fundamental uncertainty of tiny particles and fields. For decades, the two frameworks coexisted, each powerful in its own realm. But at extreme scales, near singularities or in the universe's earliest moments, their domains overlap, and smooth spacetime begins to fracture. Observations from NASA's Event Horizon Telescope and Chandra X-ray Observatory show this vividly. Near the boundary of a black hole, curvature becomes extreme, and the familiar fabric of space and time bends almost beyond recognition. And yet, even at these extremes, the universe whispers order. Patterns persist, laws endure. Photons trace paths that reveal the hidden structure, guiding our understanding. Space is alive, dynamic, yet disciplined. It is neither empty nor chaotic. It is a canvas of subtle movement, constrained by principles older than our observation, but visible to those who look carefully. As you let this unfold, imagine yourself drifting alongside a photon, gliding over the ripples of spacetime. Feel the silent pulse of the universe beneath you, a harmony of motion and restraint, uncertainty and law. Allow your mind to relax into the rhythm of cosmic order, the gentle coherence that stretches from the tiniest scales to the farthest galaxies. The universe is awake, but it moves with patience and care, and so can you, here, in your quiet moment, letting this cosmic story settle softly around you. In the classical view, geometry speaks in certainties, predicting points where curvature grows without limit, singularities that signal not triumph, but the edge of understanding. They mark where the rules we trust must yield to something deeper. On another front, quantum fields whisper their own warnings. As we peer at ever smaller scales, fluctuations swell, energy becomes elusive, and calculations diverge unless artificial cutoffs are imposed. These divergences are not accidents. They are nature's way of telling us that smoothness cannot endure forever. The Planck scale emerges quietly, almost reverently, as the threshold where both classical and quantum expectations falter. Below this scale, geometry cannot remain smooth, and spacetime itself refuses to be treated as a calm backdrop. Here, distances and durations lose their independence, dissolving under the weight of energy and uncertainty. Observations of the early universe hint at this truth. The cosmic microwave background, mapped by the Planck satellite, reveals patterns consistent with quantum origins yet guided by the broad sweep of geometry. Light from galaxies captured by the James Webb Space Telescope, formed less than 1 billion years after the Big Bang, tells the same story. Structure emerged quickly, ordered and beautiful, implying that space and quantum fields dance together under extreme conditions that neither theory alone can fully describe. Yet the cosmos maintains its calm on larger scales. Gravitational waves detected by LIGO ripple gracefully across millions of light-years, and light from distant quasars arrives with clarity, its spectral lines sharp and unwavering. Even as the Planck scale looms far below direct observation, the universe imposes order. Whatever lies beneath smooth geometry, it must reconcile with the broad coherence we witness, preserving harmony while hiding its deeper rhythm. Physicists have proposed many ways to understand this frontier. Some imagine spacetime as a network of discrete, fundamental units, woven like a delicate lattice. Others see geometry emerging from relationships of quantum information, a tapestry of connections rather than a fixed fabric. Every approach honors a single truth: spacetime cannot remain continuous down to the smallest scale. The Planck length is not an arbitrary invention, it is a boundary imposed by the convergence of principles we have come to trust. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." Here, those words feel almost literal. The limits of smooth spacetime are not a mystery added to physics, they are a rule revealed by the consistency of what we already understand. Distance cannot be subdivided endlessly, duration cannot be refined without consequence, and events cannot always be separated with perfect clarity. These are not mistakes, they are the language of nature itself. And then comes the question: what happens when quantum mechanics is applied not to particles within space, but to spacetime itself? Gravity, unlike other forces, is the stage, not an actor upon it. When uncertainty touches geometry, smooth curves dissolve into a restless, shifting landscape. Distances wobble. Curvature fluctuates. John Wheeler, in the 1950s, realized that if spacetime is treated as a quantum object, it cannot remain calm. He called this realm quantum foam, a technical term for a universe that trembles and ripples at the tiniest scales. In classical physics, between any 2 points lies always another, and distances can be divided endlessly. This principle supports Newton, Einstein, the elegance of smooth general relativity. But quantum mechanics forbids infinite precision. Applied to spacetime, this means geometry cannot remain fixed. Curvature dances. Topology shifts. Space is alive in ways we cannot directly see. The Planck length returns as a guardian of limits. Around 1.6 times 10 superscript 3 meters, attempting to confine energy further begins to warp spacetime itself. Measurement and influence become inseparable. Below this scale, classical notions of space cease to hold. Wheeler's insight was not speculation, it was consistency. Quantum uncertainty and gravitational response intersect, producing a frothy, fluctuating stage. Later studies reinforced his vision. Attempts to apply perturbative quantum gravity revealed divergences that could not be renormalized away. Unlike electromagnetism, gravity refuses simplification. The smooth fabric is pushed beyond its domain of validity. And yet, the cosmos remains disciplined. Light traveling billions of light-years preserves coherence. Quasars reveal interference patterns. Gamma-ray bursts show no energy-dependent delays. The foam is there, but it hides, averaging out, maintaining the universe's harmony. Different approaches to quantum gravity paint this picture in distinct colors. Loop quantum gravity imagines discrete patches of space and volume. Causal dynamical triangulations assemble spacetime from simple building blocks obeying strict rules. String theory smooths interactions at the tiniest scales, redefining the texture of reality itself. All share a single goal: explaining why smooth spacetime works where it does, and why it must yield where it cannot. Photons, ever faithful, act as subtle witnesses. Their paths are shaped by geometry. They integrate every curve and fluctuation, revealing the extraordinary coherence of the cosmos. So far, they show no sign of violent disruption. Their light is guidance, a quiet message that whatever quantum spacetime may be, it preserves order with astonishing efficiency. Fluctuations exist, but they are structured, confined, obeying principles that safeguard causality, locality, and symmetry at scales we can measure. At the Planck scale, the sharp distinction between events softens. Paths once distinct merge and shift, connections appear and dissolve, yet even here, there is rule, not randomness. The foam is structured uncertainty, a hidden choreography beneath the calm surface. And history reminds us, every time classical concepts are stretched beyond their limits, they fracture. Absolute simultaneity collapsed with relativity, deterministic trajectories dissolved with quantum mechanics, and now smooth spacetime yields to quantum gravity. Yet physics is not destroyed. It deepens. It becomes richer, revealing a universe alive, restless, yet infinitely coherent. Carl Sagan once reflected, "Science is a way of thinking much more than it is a body of knowledge." In this gentle way of thinking, space-time itself becomes a subject, not a sacred backdrop, open to inquiry and understanding. Observations from NASA and ESA missions guide us in this disciplined view. Gravitational waves ripple across vast cosmic distances with fidelity. Light travels with unwavering coherence. Large-scale geometry behaves with quiet consistency. These facts anchor everything we can trust. Quantum foam is not a fanciful idea. It is the inevitable consequence of applying quantum principles to gravity with honesty. Whether it takes the form Wheeler imagined or a subtler structure yet to be discovered, one thing is clear: smooth spacetime cannot be fundamental. Geometry becomes active. Locality softens into approximation. The universe's structure is no longer a silent stage for photons to traverse. It becomes a responsive, living environment, subtle yet persistent in its influence. Even as spacetime stirs at its foundation, quantum fields continue their quiet propagation, forcing us to distinguish between the restless geometry of space itself and the fluctuations of the fields it hosts. This is an essential separation. Part 4 begins with a question: why aren't quantum vacuum fluctuations the same as spacetime foam? The answer lies in a subtle but vital distinction. Vacuum fluctuations emerge from quantum field theory. Fields exist everywhere, and even in their lowest energy state, they cannot rest completely. They retain motion, enforced by the uncertainty principle, and these fluctuations are measurable, influencing particle properties, atomic transitions, and forces between objects. Yet, these ripples occur on top of spacetime. The stage itself remains smooth, untouched. Spacetime foam, by contrast, arises only when gravity is treated as a quantum phenomenon. Here, the stage itself trembles. Geometry becomes the object that fluctuates, not just the fields upon it. Confusing these two realities collapses a crucial distinction, leading to misunderstandings about energy, causality, and the very connection between events. History guides us gently through this truth. Quantum field theory, crafted in the mid-20th century to reconcile special relativity with quantum mechanics, achieves unmatched success. Predictions from quantum electrodynamics align with experiments to better than 1 part in a trillion. The theory assumes a fixed spacetime, a well-defined backdrop in which fields exist and particles emerge. Vacuum fluctuations, born from the impossibility of perfectly defining energy and time simultaneously, are an inherent feature of this framework. The Casimir effect provides a vivid demonstration. Two uncharged plates, separated by mere micrometers in a vacuum, attract one another. This force does not arise from hidden charges or residual gas. It arises because the electromagnetic field cannot sustain the same spectrum of fluctuations between the plates as it can outside. Geometry constrains the field. Energy shifts, and a force appears. Spacetime itself, however, remains calm and unyielding. This distinction holds across all quantum field theory. Virtual particles, vacuum polarization, and zero-point energy describe field behavior within spacetime. None require spacetime itself to fluctuate. None introduce uncertainty into distances or durations. Spacetime foam is a different story. When gravity is quantized, geometry itself becomes uncertain. Distances, areas, and volumes are subject to quantum fluctuations. Wheeler grasped this in the 1950s, realizing that applying uncertainty to spacetime destabilizes classical continuity. At sufficiently small scales, geometry fluctuates violently, and he named this domain quantum foam. These are not fluctuations within spacetime, they are fluctuations of spacetime itself. Observational evidence reinforces this separation. Light from distant quasars preserves interference patterns. Gamma-ray bursts monitored by NASA's Fermi telescope show no significant energy-dependent delays. Gravitational waves travel coherently across millions of light-years. At large scales, spacetime remains smooth, orderly, and disciplined. Vacuum fluctuations exist, but they average out. Foam, if it exists, is confined to scales far beyond direct observation. Confusing these two regimes often leads to exaggerated claims. Vacuum energy, sometimes invoked in discussions of dark energy, arises within fixed geometry and does not imply spacetime instability. Spacetime foam, by contrast, asks how geometry itself behaves under quantum principles. It does not equate field activity with geometric chaos. Entanglement offers another illustration. Quantum fields can be entangled across space-like separations without requiring spacetime itself to fluctuate. Foam, however, could blur locality at the tiniest scales, altering the structure of connections between events. Maintaining this boundary preserves clarity in physics. Fields fluctuate within spacetime, geometry fluctuates when gravity is quantum. Mixing them leads to missteps in understanding causality and information flow. Modern theories of quantum gravity honor this boundary. Loop quantum gravity quantizes geometric quantities directly, giving discrete areas and volumes. Causal dynamical triangulations build spacetime from simple blocks, where geometry itself is the fluctuating entity. Across approaches, the motivation is unified. Smooth spacetime cannot endure when quantum mechanics is applied to gravity. Something deeper underlies it, subtly guiding fields and particles while allowing the universe to appear serene and coherent at large scales. String theory takes a different path, yet the essential distinction remains. Quantum fields exist upon extended objects, subtly shaping spacetime at the tiniest scales. Even if the background itself becomes dynamic, the difference between the restless activity of fields and the fluctuations of geometry is preserved. Vacuum fluctuations are not the same as spacetime foam. They cannot be, for conflating them would unravel the logical foundation of the theories we trust. Observations guide this careful separation. Photons travel across cosmic distances without losing coherence. Atomic clocks tick in perfect synchrony. Interferometers capture gravitational waves with precise phase relationships. None of this would be possible if spacetime itself roamed wildly at observable scales. Any foam that exists must hide, influencing physics only indirectly, through subtle effects that average out, preserving symmetry, causality, and the deep order we observe. Spacetime foam is not a metaphor. It does not mean that space is energetic or busy. It is a precise consequence of applying quantum uncertainty to geometry, rather than to fields. It represents a layer beneath the one we explore with quantum field theory, a deeper structure guiding the universe quietly, almost imperceptibly. And because it lies beneath the stage of measurement itself, its effects remain hidden, averaged, and constrained by the very structure it gently destabilizes. Carl Sagan once wrote, "Extraordinary claims require extraordinary evidence." The extraordinary claim that spacetime itself fluctuates demands extraordinary proof. So far, the universe has offered none that contradicts the smoothness we observe. Only theories that respect the boundary between fields and geometry survive contact with data. And here we find ourselves facing something deceptively simple: light. Every photon is a messenger, guided by geometry, carrying whispers of spacetime's smallest structure. Part 5 begins with this truth. Photons are the most sensitive witnesses of spacetime. A single photon can cross the observable universe without pause, without slowing, never separating itself from the geometry it moves through. Unlike any other object, it is inseparable from motion itself. Photons have no rest mass. This is not merely a label, but a profound physical constraint confirmed by every experiment. With no rest frame, a photon cannot be stationary. It is always in motion, its path inseparable from the curvature of spacetime. Where massive objects follow trajectories shaped partly by inertia, photons follow geometry itself with absolute fidelity. Even the smallest bend or curve leaves its mark on their journey. This sensitivity is visible in the cosmos. Gravitational lensing, predicted by Einstein and first observed during the 1919 eclipse, shows light bending around mass. NASA and ESA have since traced arcs and rings formed by distant galaxies, revealing the hidden scaffolding of dark matter. Matter responds to gravity. Light traces geometry. Because photons have no mass, they cannot smooth over irregularities. Every subtle deviation leaves its imprint. Across cosmic distances, this role becomes extraordinary. Photons observed by the James Webb Space Telescope may have traveled over 13 billion years, crossing expanding spacetime, regions of varying curvature, and environments filled with quantum fields. If spacetime held small-scale irregularities that did not average out, these photons would carry the record. And so astronomers watch carefully, analyzing coherence with astonishing precision. Spectral lines from distant atoms remain sharp. Interference patterns endure. Photon arrival times across vast energy ranges remain tightly correlated. Gamma-ray bursts provide a particularly revealing test. They release immense energy in brief flashes, spanning a wide spectrum of photons. NASA's Fermi Gamma-ray Space Telescope monitors bursts from billions of light-years away. If space-time fluctuations accumulated, photons of different energies would arrive at slightly different times. They do not. Differences remain smaller than milliseconds, even after billions of years of travel. The universe allows activity, yet enforces coherence. Quantum mechanics deepens this story. Photons, wave-like and entangled, exhibit interference that is exquisitely sensitive to path differences smaller than the width of an atom. If spacetime fluctuated violently at small scales, coherence over cosmic distances would be impossible. The fact that it persists suggests that any micro-irregularities are tightly constrained. The geometry cannot introduce random phase noise without violating observation. Photons, in this light, are more than messengers. They are probes of spacetime itself. Their journeys carry information about the medium they traverse, even when that medium is geometry itself. Absence of distortion is as telling as its presence. Historically, this role was not immediately clear. Early quantum theory treated light primarily as a carrier of energy. Einstein's photoelectric explanation emphasized quanta, not geometry. Only with relativity did the full significance of light's sensitivity emerge. Later, quantum electrodynamics refined this picture. Vacuum polarization, photon scattering, and loop corrections showed that photons interact even in empty space. Yet all of this unfolds in a fixed geometry. When geometry itself becomes subject to quantum uncertainty, photons occupy the boundary between what is known and what is still a mystery. NASA's Cosmic Background Explorer, WMAP, and ESA's Planck satellite reveal yet another layer. Photons from the cosmic microwave background, last scattered when the universe was 380,000 years old, preserve information about early spacetime geometry. Tiny temperature variations encode density fluctuations and curvature conditions of that time. These patterns remain coherent across the sky, confirming that even under extreme early conditions, spacetime behaved in a disciplined way. James Webb extends this story further. Observing galaxies formed within the first billion years, it captures photons that experienced early spacetime under intense conditions. Their properties constrain the geometry's behavior at small scales, offering clues about the subtle structure that underlies the universe. Theoretical models of spacetime foam must satisfy these exacting conditions, ensuring that geometry, though restless at its foundation, preserves coherence across the cosmos. Microscopic fluctuations may exist, but they leave no chaotic trace. They preserve Lorentz symmetry at scales we can observe. They allow photons to remain precise witnesses of the universe's geometry. Some theories imagine spacetime built from tiny, discrete units. Others propose that geometry emerges from deeper quantum relations. In every case, photons serve as silent testers. Any model that predicts distortions inconsistent with what we see is ruled out. This is why photons occupy a unique place in the cosmos. They are not just messengers from distant galaxies. They are diagnostic instruments for spacetime itself. They respond directly to geometry, without the buffering effects that protect massive particles from small-scale irregularities. Yet photons are remarkably forgiving. Their sensitivity does not amplify every tiny disturbance into chaos. Instead, it integrates the universe's structure with coherence, preserving order across unimaginable distances. Carl Sagan once said, "The universe is under no obligation to make sense to you. For photons, the universe does not simplify. It records every detail faithfully. It is our task to read the story they carry. If spacetime fluctuates at the smallest scales, how do those fluctuations interact with quantum coherence? How does geometry remain both active and disciplined? Photons continue to provide clues. Every observation narrows possibilities. Every constraint removes entire classes of models. The absence of distortion becomes evidence itself. Here, expectation meets subtle restraint. Photons travel faithfully through geometry, yet the universe keeps its secrets well hidden. Why should quantum foam leave traces on light crossing billions of light years? If spacetime fluctuates at microscopic scales, photons cannot escape unaltered. Light follows geometry with absolute fidelity. Any microscopic irregularity leaves a faint trace. For journeys of a few meters or even kilometers, these effects are undetectable. But the universe offers distances far beyond the laboratory, where even tiny effects could, in principle, accumulate. In models of foamy spacetime, photons may experience minuscule fluctuations in effective distance along their path. These shifts are constrained by symmetry, causality, and the laws we know. Yet they could introduce tiny phase shifts. Phase is not abstract. It determines whether waves interfere constructively or destructively. Laboratory experiments detect shifts smaller than a single wavelength. Astronomical observations extend that sensitivity across billions of years. If spacetime foam introduced uncorrelated phase noise, interference patterns would blur, spectral lines would soften, images would degrade. Yet they remain sharp. This absence of distortion imposes one of the strongest constraints on quantum gravity models. It does not rule out foam entirely, it merely bounds it. Some models predict phase noise growing linearly with distance. Others grow like a random walk. Some saturate beyond a certain scale. Observations eliminate the strongest versions, leaving room only for subtle, tightly constrained effects. NASA's Hubble Space Telescope revealed more. Diffraction-limited images of distant quasars remain sharper than many foam models allow. Those models were eliminated. Gamma-ray bursts add another layer. Emitting photons across vast energies in brief flashes, they allow direct tests. High-energy photons arrive nearly simultaneously with low-energy ones, even after traveling over 10 billion years. The strongest dispersive effects are ruled out. Only the faintest, most disciplined fluctuations survive. Angular deflections offer a complementary probe. If spacetime fluctuates, photon directions could wander. Very long baseline interferometry combines telescopes across Earth to detect even the tiniest shifts. Images of distant quasars remain sharply defined. Any angular wandering must be extraordinarily small. Energy-dependent delays, phase coherence, angular stability, all converge on the same lesson. If spacetime foam exists, it is balanced. It matters at fundamental scales, yet it leaves the universe coherent at scales we observe. This balance is not random. It preserves Lorentz symmetry at accessible energies. Special relativity remains intact, even if spacetime's deepest layers are restless. Some theories propose strongly correlated fluctuations, canceling out over vast distances. Others restrict effects to directions transverse to photon travel. Still others suggest quantum geometry interacts with light to preserve average speed. Observations of the cosmic microwave background reinforce these constraints. Photons that last scattered 380,000 years after the Big Bang preserve density fluctuations with extraordinary precision. Any uncontrolled foam-induced noise would erase these patterns. Yet they remain intact. ESA's Planck mission measured temperature fluctuations down to microkelvin scales. JWST extends this record, capturing photons from the first billion years, traveling through extreme early conditions. No loss of coherence, no unexplained dispersion. The picture is clear. Light is exquisitely sensitive to spacetime, yet the universe maintains coherence across cosmic scales. Spacetime foam, if it exists, is not chaotic. It is structured, disciplined, and bounded. Fluctuations may exist at the smallest scales, but they average out with extraordinary efficiency. Theoretical models that survive observation replace smooth geometry with discrete or relational structures that reproduce classical behavior when viewed at large scales. Photons interact with effective geometry rather than individual microscopic elements, preserving the information we can measure. History offers a reminder. Before atoms could be imaged, their existence was inferred from spectral lines. In the same way, spacetime foam may reveal itself only indirectly, through subtle, faithful messages carried by photons. Carl Sagan once observed, "Somewhere, something incredible is waiting to be known." Here, that waiting is enforced by nature itself. The traces are faint by design. They test both instruments and theoretical restraint. The absence of dramatic effects is not failure. It is a profound result. It tells us that the universe is coherent at scales where coherence matters. It tells us that any deeper structure must honor the stability we observe. Every photon that crosses the cosmos is both messenger and probe. Each observation narrows possibilities, eliminates models, and sharpens understanding. Precision speaks through absence. Light arriving from quasars billions of light-years away without the signatures of quantum foam silently teaches us about spacetime's hidden order. Part 7. How distant quasars ruled out many quantum foam models. Some of the most decisive experiments in physics were never built by human hands. They were carried out by the universe itself, across distances no laboratory could ever reproduce. Long before detectors were refined, long before theories were debated, light had already begun its journey, carrying a silent record of what spacetime allowed and what it did not. Quasars are among the most extreme beacons in the cosmos, powered by supermassive black holes devouring matter at the hearts of young galaxies. They radiate enormous energy across the electromagnetic spectrum. Many quasars we observe today are more than 10 billion light-years away. The photons reaching us began their journey when the universe was a fraction of its current age. From the perspective of quantum gravity, these photons are priceless. They have traversed most of the observable universe, crossing expanding spacetime, gravitational wells, intergalactic plasma, and whatever microscopic structure spacetime may hold. If quantum foam introduced cumulative distortions, quasars would reveal it. Early models predicted that tiny, random fluctuations in spacetime would shift a photon's phase or direction. Individually negligible, these effects would accumulate over billions of years, smearing interference patterns, blurring images, or creating energy-dependent distortions. Astronomers knew where to look. High-resolution imaging from the Hubble Space Telescope allowed them to examine quasars with extraordinary angular precision. These distant objects act as perfect point sources, revealing any angular wandering caused by spacetime. The results were decisive. The images were impossibly sharp. Interference fringes remained intact. Angular coherence persisted far beyond what many quantum foam models predicted. Entire classes of models failed quietly. No dramatic headlines, no sudden revolution, simply nature refusing to cooperate with theory. Models predicting linear or random walk accumulation of fluctuations were incompatible with observation. Gamma-ray bursts added another layer. These brief, intense flashes originate from massive stellar collapses or neutron star mergers, releasing photons across wide energy ranges in milliseconds. If quantum foam caused energy-dependent variations in speed, high-energy photons would arrive earlier or later than low-energy ones. NASA's Fermi Gamma-ray Space Telescope measured them directly. Across multiple bursts, photons arrived nearly simultaneously. The universe had tested the theory, and it failed to produce the expected delays. This pattern repeated across observational platforms. Very long baseline interferometry linked radio telescopes worldwide, detecting angular deviations far smaller than a single instrument could. Distant radio quasars remained stable. Phase coherence persisted. Spacetime, whatever its hidden structure, preserved macroscopic order with extraordinary fidelity. The cosmic microwave background offered yet another constraint. Photons from 380,000 years after the Big Bang preserve density fluctuations and curvature with astonishing precision. ESA's Planck mission mapped them across the entire sky. Any uncontrolled phase noise or angular distortion would have erased these patterns. They survived. The message is clear: simple models of quantum foam are not compatible with reality. What survives are models in which fluctuations are highly constrained, correlated, or suppressed, preserving large-scale coherence. Quantum foam, if it exists, is no chaotic turbulence. It obeys strict rules, even if those rules emerge from deeper layers of spacetime. The universe tolerates no excess noise. Photons arrive on time. Images remain sharp. Interference persists. The path forward is narrow. Only a few forms of quantum spacetime remain viable, those that preserve the behavior of light itself. Part 8. Why the speed of light survives spacetime fluctuations. If spacetime truly fluctuates at the smallest scales, the constancy of light should have been the first casualty. Yet, observation tells a different story. Across laboratories, across galaxies, across billions of years, light travels at the same invariant speed. Not approximately, not on average, but precisely. This persistence is no coincidence. It is a constraint that any theory of quantum spacetime must respect. The speed of light is more than the velocity of photons. In Einstein's relativity, it is the conversion factor between space and time. It defines causal structure, determining which events can influence others and which remain forever separate. Relativity has been tested relentlessly. Atomic clocks flown in aircraft and satellites tick exactly as predicted. Particle accelerators function because relativistic timing holds. Signals exchanged with spacecraft arrive precisely on schedule. NASA's Deep Space Network relies on this constancy to navigate probes across billions of kilometers with meter-scale accuracy. If spacetime fluctuations altered light even slightly, these systems would fail. They do not. Quantum gravity initially suggested a challenge. If distances and durations fluctuate at microscopic scales, why does light maintain its speed? Some early foam models predicted scattering or energy-dependent delays. In these models, light speed was only approximate. Nature rejected them. Gamma-ray bursts provided a definitive test. Photons across wide energy ranges arrive simultaneously even after billions of years. Distant quasars reinforce this conclusion. Spectral lines remain sharp. Interference patterns persist. The universe preserves the speed of light with extraordinary discipline. The resolution lies in organization. Random, uncorrelated irregularities would scramble photons. But quantum gravity does not permit arbitrary randomness. Any viable theory must reproduce Lorentz symmetry at observable scales. This symmetry is not an aesthetic choice. It is one of the most precisely tested principles in physics. Particle accelerators, atomic clocks, and astrophysical observations constrain violations to parts per billion. The absence of violation is itself powerful evidence. This does not imply spacetime is smooth at all scales. It implies that fluctuations, if present, are constrained so that symmetry emerges when averaged over larger distances. Smoothness becomes effective rather than fundamental. Analogies from condensed matter help. A crystal lattice breaks continuous symmetry microscopically, yet waves propagate through it, obeying perfect symmetry at long wavelengths. Spacetime may behave similarly. Microscopic structure can exist without disrupting macroscopic symmetry. The speed of light remains invariant because it is enforced by deeper constraints, arising from the hidden order of spacetime itself. Part 9. Why spacetime might be built from discrete structures. At a certain point, smooth spacetime stops cooperating with physics. It does not crash noisily or catastrophically. It simply refuses to remain mathematically consistent when pushed to the smallest scales. That refusal is the reason this question exists at all. For over a century, physics treated spacetime as a continuum. In Einstein's general relativity, spacetime is smooth by construction. Curvature varies from place to place, yet between any 2 points, infinitely many others exist. Distances and durations can be subdivided without limit. This assumption worked beautifully. It predicted gravitational lensing, time dilation, black holes, and gravitational waves, all confirmed by observations from NASA, ESA, and ground-based observatories. Quantum mechanics introduced a different lesson. Energy comes in discrete quanta. Atomic transitions occur in steps. Angular momentum is quantized. These were not philosophical choices, they were demanded by experiment. When physicists tried to apply similar quantization to gravity, continuity itself became a liability. The problem emerges near the Planck scale, roughly 1.6 times 10⁻³ times 10 carat minus 35, 1.6 times 10⁻35 meters. Attempting to localize events at these scales requires enormous energies, so large that spacetime curvature can no longer be ignored. Classical geometry assumes that spacetime exists independently of what occupies it. Quantum gravity denies that separation. Measurement itself disturbs geometry. If geometry is subject to quantum uncertainty, treating it as infinitely divisible becomes questionable. The continuum may not be fundamental. Something must give. This insight inspired multiple independent approaches, all rejecting smoothness as a starting point. Loop quantum gravity begins by reformulating general relativity in a quantizable way. Geometry is no longer a smooth field but a network. Space is composed of nodes connected by links, forming spin networks. These networks are not embedded in spacetime, they are spacetime. Areas and volumes take discrete values, much like energy levels in an atom. There is a smallest possible area, a smallest possible volume. Below these scales, geometry cannot be subdivided. This discreteness emerges naturally from the theory. At large scales, the collective behavior of many such units reproduces the smooth geometry we observe. Causal dynamical triangulations take a different route. Instead of quantizing geometry directly, spacetime is assembled from simple building blocks, higher-dimensional analogues of triangles and tetrahedra, glued together following strict causal rules. Random assembly produces chaos, but enforcing causal order yields a well-behaved spacetime at large scales. Small-scale geometry may appear highly irregular, yet smoothness emerges statistically. Continuity is not fundamental. It is emergent. Holographic approaches offer yet another vision. Inspired by black hole thermodynamics, the holographic principle suggests that the information content of a spacetime region is proportional not to its volume, but to its boundary area. Through the ADS/CFT correspondence, geometry in higher dimensional space emerges from quantum information on a lower dimensional boundary. Here, spacetime is not made from geometric pieces at all. It is built from patterns of entanglement. Distance corresponds to correlations. Geometry reflects information structure. Smooth spacetime arises when entanglement takes the right form. Across all these frameworks, continuity is replaced with something deeper: networks, simplices, or patterns of quantum information. Observations constrain them. Gravitational waves propagate coherently across millions of light years. Light from distant quasars remains sharp after billions of years. Any underlying discreteness must average out efficiently at large scales. Discrete does not mean jagged or noisy. Atoms do not make solids rough, they make them stable. Likewise, discrete spacetime could underlie smooth geometry without disrupting observable physics. Historical parallels are instructive. In the 19th century, matter was assumed continuous. The discovery of atoms changed that understanding. Fluids remained smooth at everyday scales. Thermodynamics remained valid. But the underlying reality had changed fundamentally. Spacetime may be undergoing a similar transition. Carl Sagan once remarked, "We are made of star stuff." In a deeper sense, spacetime itself may be made of something else, something that does not resemble space or time as we know it. This is not poetic speculation. It is a recognition that fundamental descriptions often look nothing like the phenomena they explain. Part 10. How spacetime shapes reality. No existing theory has the final word. Each framework competes, overlaps, and challenges the others. They are measured not by elegance alone, but by their ability to reproduce known phenomena while remaining self-consistent. What stands out now is that smooth geometry is no longer assumed. It emerges. It appears only when deeper patterns in spacetime fall into place. This realization changes the way we ask questions. Instead of wondering why spacetime fluctuates, physicists now ask what it is made of. Instead of treating geometry as a given, they treat it as something that arises from more fundamental ingredients. Observations continue to refine the picture, quietly removing some models and allowing others to persist. The process is subtle, like the silent verdict of photons traveling from the farthest reaches of the cosmos. All the evidence points to one profound truth: reality is structured by spacetime itself, not by particles, forces, or energy first. Before matter can exist, before energy can move, before cause can produce effect, spacetime dictates the rules. And if those rules changed, the universe built upon them would be entirely different. We return to photons because they have never stopped their journey. Light from the earliest stars, from galaxies captured by the James Webb Space Telescope, from quasars whose radiation began more than 10 billion years ago, arrives intact. These photons carry more than images. They carry a record of the medium they crossed, a testament to what spacetime allowed. Photons interact directly with geometry. They have no mass to shield them, no internal mechanisms to act independently. Their motion is defined entirely by the fabric they travel through. In this sense, light acts as a cosmic guide, marking the boundaries of what structures spacetime permits and forbids. Along the way, many simple assumptions have quietly failed. The idea that empty space is inert fell apart. The belief that spacetime remains smooth at every scale did not hold. The assumption that quantum fluctuations and geometric fluctuations are identical was insufficient. Even the expectation that microscopic structure would automatically disrupt macroscopic physics proved wrong. Each of these lessons was enforced not by debate, but by observation. Nature measured, and the results were clear. Photons arrive precisely on time. Spectral lines remain sharp. Interference patterns persist. Gravitational waves travel in lockstep with light. Atomic clocks stay in perfect rhythm. These facts draw firm boundaries around speculation, revealing that whatever spacetime is, it preserves coherence with astonishing fidelity. This has deep consequences. Spacetime is not just a passive stage. It actively constrains reality. Only certain forms of matter and energy can exist. Only certain interactions remain stable. Only certain structures last long enough to be observed. If spacetime were more erratic, atoms could not form. Chemistry would break down. Signals would blur. The speed of light could not serve as a reliable cosmic ruler. In short, the universe we see could not exist. Different quantum gravity theories explore these ideas in their own ways, yet they converge on a single lesson: geometry may not be fundamental, but it governs everything built upon it. Whether spacetime is woven from networks, simplices, or patterns of quantum information, its effective behavior dictates particle motion, field propagation, and correlation survival. Photons lie at the heart of this order. They move at the maximum allowed speed, define causality, and integrate the structure of spacetime along their entire path. Each photon observed is a confirmation. Each undistorted signal is a boundary enforced. The absence of dramatic quantum gravity effects is not a disappointment, it is a revelation. It tells us that spacetime is subtle, disciplined, and perfectly coherent. The frontier is not where physics collapses, but where it endures under extreme conditions. History offers perspective. Atoms were once invisible, inferred only from spectral lines, heat capacities, and chemical ratios. Matter appeared continuous, but its behavior demanded discreteness at a deeper level. Spacetime follows the same pattern. Smooth and reliable at human scales, yet at fundamental levels it cannot remain continuous without contradiction. Something beneath the surface governs the behavior we observe. As Carl Sagan observed, we live in a universe governed by chance and necessity. In this context, necessity dominates. Here, necessity is encoded in spacetime itself. It decides which fluctuations vanish, which accumulate, which structures persist, and which dissolve. Photons continue their journey largely unchanged, and that alone rules out countless possibilities. Spacetime cannot be arbitrarily noisy, granular, or asymmetrical. It must conceal its deepest structures behind order, not chaos. The frontier remains open not due to lack of imagination, but because nature enforces limits. Theories must survive scrutiny from every observation. Each new measurement tightens the constraints. Observations from the James Webb Space Telescope now probe the early universe, showing that light preserved its coherence under conditions far more extreme than those today. The picture is not complete, but it is clear. We know where simple models fail. We know where nature speaks decisively. We know where uncertainty remains. Spacetime may not be fundamental, but it is decisive. It governs what exists, what interacts, and what persists long enough to be observed. Photons will continue to arrive, silently carrying knowledge of distant sources and the structure of spacetime itself. They await better instruments, sharper theories, deeper questions. The universe does not hide its structure to confuse us, it hides it in consistency. For now, it continues to behave exactly as it always has. Light travels at its constant speed. Geometry maintains coherence. Reality unfolds within the rules spacetime allows. If you are listening at the close of a long day, or in the quiet hours as rest approaches, this is the perfect place to pause. Photons will continue on their journey, whether we watch or not. And the universe will continue to hold together, as it has across unimaginable spans of time. Let that steadiness linger in your mind, slow your thoughts, and carry you gently into sleep. Good night.